Night over a silent desert. The sky is black enough that the Milky Way looks like a river of frost, stretching from one horizon to the other. The only sound is wind over sand. A single beam of light cuts through the darkness. It sweeps over ripples of dune, over pale stones, and then stops on something that doesn't fit. Half buried in the sand lies a small, dark rock with a smooth, glassy skin, as if it has been fired in a cosmic kill. Imagine you are walking across an empty landscape. The voice says, calm and precise, and you find a rock that does not belong. You pick it up. It is heavier than it looks. The surface is dark and thinly melted, like lacquer that has run and frozen in place. Tiny regmaglyphs, thumbprint like hollows, dimple its skin. This is not just a rock. This is a meteorite, a piece of the solar system that has fallen, quietly, into your hand. We rewind its journey. Far above Earth's atmosphere, it began as a meteoroid, a small fragment of rock or metal tracing a lonely orbit around the sun. For millions, sometimes billions of years, it circled in silence, a leftover from the age when planets were still assembling. Then, one day, its orbit crossed ours. As it plunged into Earth's atmosphere at tens of kilometers per second, air in front of it compressed and heated to incandescent temperatures. The meteoroid flared into a meteor, a bright streak of light burning across the sky. Most objects like this never reach the ground. They vaporize completely in a second or two. But this fragment was large, dense, and tough enough to survive. The outer layer melted and flowed, then froze into a thin fusion crust as the object slowed down in the lower atmosphere. Finally, no longer a meteoroid or a meteor, it became something else, a meteorite, resting on the surface of a world it did not come from. That is what lies in your palm. Meteorites are different from anything we can pick up elsewhere on Earth for one simple reason. They are samples from other worlds that arrive by themselves. No launch vehicle, no re-entry capsule, just gravity, rock, and time. Some meteorites are older than any rock on this planet. Earth's surface is constantly recycled by plate tectonics, volcanism, and erosion. The oldest intact terrestrial rocks are about 4.0 billion years old. Many meteorites preserve minerals that solidified more than 4.5 billion years ago, in the very first few million years of the solar system's history. They are time capsules from an era our planet has long since erased. And they come from specific places. Most meteorites began inside asteroids, small, primitive worlds that never grew large enough to become full planets. Some fragments can be traced back to differentiated bodies with metallic cores and rocky mantles, smashed apart in catastrophic collisions. A few rare meteorites carry the chemical and isotopic signatures of the Moon. Others, rarer still, match Mars, launched into space by giant impacts and eventually captured by Earth's gravity. In your hand might be a shard of an ancient rubble pile in the asteroid belt, or a chip of a long-dead volcanic surface on the Moon, or a piece of Martian crust that watched dust storms sweep across a sky of two tiny moons. Holding a meteorite is holding evidence. Evidence of the temperatures and pressures in the early solar nebula. Evidence of the way dust grains stuck together and melted into droplets of rock. Evidence of when water and organic molecules first infiltrated small bodies long before there were oceans here. In this episode, we will follow these fallen stones from the moment they ignite the night sky to the moment they cut into a scientist's thin section under a microscope. We will see how their textures, minerals, and isotopes have rewritten what we thought we knew about. How and when the planets formed. Where Earth's water and carbon-rich material came from. And what ingredients were present before life ever appeared on this world. For now, we stay with that single, quiet moment in the desert. A human hand. A dark stone, still faintly cold from the night. And the realization that you are not just picking up a rock, you are picking up a fragment of a broken world, older than any mountain, carrying a message written in minerals and metal, sent across space and time to land at your feet. If you pick up a random rock on Earth, it tells you something about this planet. If you pick up a meteorite, it can tell you which world it came from, and which layer of that world you are holding in your hand. In planetary science, we divide meteorites into three broad families: stony, iron, and stony iron. Within those simple words is an entire anatomy of forming planets. 1. Stony meteorites, the most common and the most ancient. Most meteorites are stony, dominated by silicate minerals. But even within stones there are two very different stories: chondrites and achondrites. Chondrites, snapshots of the solar nebula. Chondrites take their name from chondrules, tiny, round droplets of once molten rock frozen into the meteorite like beads in concrete. These chondrules formed very early in solar system history, when dust in the solar nebula was briefly flash-heated, melted into droplets, and then cooled and solidified while still drifting in space. Two key subgroups matter for our story. Ordinary chondrites. These are the most common meteorites that fall to Earth. They record moderate heating and mixing inside small asteroidal bodies. Their minerals show that their parent asteroids were warmed enough to alter and partially recrystallize their interiors, but not enough to fully melt and separate into core, mantle, and crust. In other words, ordinary chondrites are the middle ground, not completely pristine, not fully processed, a record of early, incomplete planetary cooking. Carbonaceous chondrites. These are darker, more fragile, and far richer in carbon and volatile elements. Many contain hydrated minerals, evidence of past liquid water, and complex organic material. Chemically, some of them are the closest we have to the bulk composition of the solar nebula, minus the hydrogen and helium that went into the Sun and giant planets. Carbonaceous chondrites are our best samples of extremely primitive material, the starting mix from which the rocky planets were built. When you look at a thin section of a chondrite under a microscope, you are seeing frozen droplets and fine dust that once floated in the young solar system's disk before any planet fully existed. Achondrites, stones from worlds that melted. Achondrites look more like terrestrial igneous rocks. They do not have chondrules. Their textures show that they have been through melting, flow, and solidification on a parent body. They come from small worlds that got hot enough, through radioactive heating and impacts, to differentiate. Heavy metal sinking inward, lighter silicates rising outward. Achondrite sample. Crustal lavas, basaltic flows that once erupted onto the surface of an asteroid or protoplanet. Shallow intrusions and mantles, coarse-grained rocks that cooled slowly below the surface. Impact melts, rocks that were remelted and mixed by violent collisions. Some achondrites can be linked to specific parent bodies. A well-known example is the HED family, tied to asteroid Vesta. These are literal fragments of another world's crust and mantle, delivered to Earth by chance. 2. Iron meteorites, pieces of planetary hearts. If you slice through an iron meteorite, polish it, and etch it with acid, a striking pattern appears, crisscrossing metallic bands called Widmanstätten patterns. These interlocking crystals of iron are nickel formed as a large metallic mass cooled extremely slowly, over millions of years. That slow cooling only makes sense deep inside a substantial body, the metallic core of a differentiated planetesimal or protoplanet. Iron meteorites are therefore interpreted as exposed cores of once larger objects. Long ago, these bodies separated into metal-rich centers and rocky mantles. Later, catastrophic collisions shattered them. Some of the core fragments were launched into space, wandered for eons, and eventually fell to Earth. Holding an iron meteorite is as close as we can currently come to holding a piece of a planetary core in our hands. 3. Stony iron meteorites, cross-sections through an interior. Between stones and ions lies the rarest and most visually spectacular group, stony iron meteorites. The most famous subtype is the pallasite, clear to greenish olivine crystals, the same mineral that makes up much of Earth's upper mantle, suspended in a shiny metal matrix. Cut and polished, they look like stained glass set in steel. Their mixed composition suggests they come from core and mantle boundaries in differentiated bodies. Metal from the core, silicate crystals from the overlying mantle, locked together in a region that was partially mixed or disrupted by impacts. Other stony ions, like mesosideриtes, are breccias, chaotic mixtures of silicate and metal fragments welded together. They, too, record violent mixing in bodies that had already developed internal layers. Stony iron meteorites are literal cross-sections through the interior structure of early planets and large asteroids, part metal, part rock, all history. 4. Where they come from, mapping the solar system through falling stones. Most meteorites originate in the asteroid belt between Mars and Jupiter. There, countless small bodies orbit the Sun. Over time, they collide. Some collisions shatter asteroids and create families of fragments sharing similar orbits. Subtle forces and gravitational nudges then slowly change those orbits until a tiny fraction of fragments' paths intersect Earth's. A very small number survive atmospheric entry. Those that reach the ground become the meteorites in our collections. By studying their chemistry, mineralogy, and isotopes, we can link different meteorite classes to different regions and depths of their parent bodies. Chondrites, primitive, undifferentiated material from asteroids that never fully melted. They are our samples of the raw building blocks of rocky planets. Achondrites, crusts, mantles, and impact melts from partially or fully differentiated small worlds. Iron meteorites, central cause of those worlds. Stony ions, mixed zones at core, mantle boundaries, or violently mixed interiors. Together, they give us a three-dimensional view of planetary construction, sliced into small, hand-sized pieces. But not all meteorites hail from the asteroid belt. Lunar meteorites, fragments of our own moon. A subset of meteorites has compositions and textures indistinguishable from lunar rocks returned by the Apollo missions. The same mineral proportions, the same isotopic signatures, the same traces of exposure to the solar wind. These are lunar meteorites, pieces of the moon's crust and upper layers blasted off by large impacts. Most eject to fall back, some go into orbit, and a tiny fraction escape the moon's gravity, enter independent orbits around the sun, and are eventually captured by Earth. They allow us to study lunar terrains beyond the Apollo landing sites, extending our knowledge of the moon's crust without launching a single new mission. Martian meteorites, rocks from a red world. Even rarer are meteorites with trapped gas bubbles whose composition matches the Martian atmosphere, as measured by landers on Mars. Their ages, mineralogy, and chemistry also fit what we know of Martian volcanic rocks. These Martian meteorites prove that large impacts on Mars can launch rocks all the way into interplanetary space. Some of those rocks wander for millions of years before intersecting Earth's orbit and falling as meteorites. In them, we see evidence of Martian volcanism and thermal history, past interactions with water and atmosphere, the internal evolution of a terrestrial planet beyond Earth. From this taxonomy, a larger picture emerges. Meteorites are not random space gravel. They are systematic samples of distinct regions and layers of small bodies, and, in the case of the Moon and Mars, of other planets. Among the thousands collected, a handful of key specimens have completely reshaped how we think about the timeline of planetary formation, the distribution of water and organics, and the internal structure of worlds we have never visited with landers. Those are the legendary meteorites we will turn to next. When you first hold a meteorite, it looks like a simple stone or lump of metal. But a few of these fallen fragments have completely rewritten our picture of the solar system. This part of the episode follows 4 of them, each a turning point in how we think about time, chemistry, impacts, and even life. 1. Allende, time capsule of the first solid grains. On the night of February 8, 1969, a bright fireball broke apart over Chihuahua, Mexico. Thousands of black stones rained down over the desert. Locals collected them. Scientists arrived quickly. The rock was named Allende, after the nearby village. Allende turned out to be a carbonaceous chondrite, one of the most primitive types of meteorite. When thin slices were examined under the microscope, something extraordinary appeared. White, irregular inclusions embedded in a dark matrix, the CAIs, or calcium or aluminium-rich inclusions. Rounded chondrules, frozen droplets that had once been molten, suspended in space. Extremely fine, dark dust in between, material close to the original solar nebula. Using radioactive dating of elements within the CAIs, scientists determined that these inclusions solidified about 4.567 billion years ago, effectively the start time for the solid solar system. That date has become the reference age for the formation of the first solids out of the Sun's protoplanetary disk. Allende also carries signatures of short-lived radionuclides, like aluminium-26, that existed only briefly at the beginning, hinting at nearby stellar events that seeded our forming system with heat-producing isotopes. Evidence of early heating and mixing, recording shock waves and localized melting in the solar nebula. Allende showed that meteorites are not random space rocks. They are layered records of the earliest processes that turned a dusty gas disk into planet-building material. In one fall, the age of the solar system stopped being an estimate and became a date you could write down. 2. Murchison, organic chemistry from the sky. Just a few months later, in September 1969, another fireball broke up over the town of Murchison in Victoria, Australia. Residents quickly collected the dark fragments. Crucially, they were picked up soon after the fall, before rain and life on Earth could heavily contaminate them. Murchison is also a carbonaceous chondrite, but of a different subtype from Allende. Where Allende is relatively rich in bright inclusions, Murchison is darker, more friable, carrying a high proportion of carbon-bearing material. When chemists began to analyze it in detail, they found dozens of amino acids, including many that are rare in terrestrial biology, a wide range of other organic compounds, simple acids, alcohols, and more complex molecules. Organic matter with isotopic fingerprints indicating it formed in space, not on Earth. The importance of Murchison is twofold. It demonstrated that complex organic chemistry is a natural outcome in small bodies formed in the outer, colder regions of the solar system. You do not need a planet, an atmosphere, or a biosphere to make amino acid-like molecules. It gave strong support to the idea that meteorites and comets could have delivered prebiotic ingredients, an expanded chemical toolkit, to the early Earth. Murchison did not prove that life came from space. What it showed, powerfully, is that the ingredients for life, the kinds of molecules biology later reproposed, arise readily in icy dust and rock exposed to radiation in interplanetary space. 3. Canyon Diablo, the rock that proved the power of impacts. In northern Arizona lies a nearly circular crater 1.2 kilometers across and about 170 meters deep, Meteor Crater, also called Barringer Crater. For decades, scientists debated whether such craters were volcanic in origin or produced by impacts. The key evidence came from a class of iron meteorites called Canyon Diablo, named after the nearby arroyo. These metallic fragments are composed mainly of iron and nickel, with a structure indicating slow cooling deep inside a large parent body. When geologists examined both the crater and the Canyon Diablo ions, several lines of evidence converged. The crater's structure and ejecta pattern matched expectations for a hypervelocity impact, not a volcanic explosion. The ions showed shock features and chemical traits consistent with having been part of a fast-moving impactor. High-pressure minerals and rocks around the crater, such as shocked quartz, could only have formed under the extreme conditions of a large impact. Canyon Diablo and Meteor Crater together settled the argument that large craters on Earth can indeed be formed by extraterrestrial impacts. Helped establish the broader concept that impact events are a fundamental geological process, not rare curiosities. That shift in thinking opened the door to later work linking giant impacts to mass extinctions, including the asteroid impact at Chicxulub associated with the end of the dinosaurs. A lump of iron in a museum display case became a key witness in a much larger story. Impacts are major sculptors of planetary surfaces and biological history. 4. ALH 84001, A Martian Rock and the Life Question. In 1984, in the Allen Hills region of Antarctica, a team collecting meteorites picked up an odd, greenish-gray rock. It was catalogued as ALH 84001. For years it was just another sample, until detailed studies of its chemistry and trapped gases revealed something striking. The gases in tiny bubbles inside ALH 84001 matched the Martian atmosphere as measured later by spacecraft. Its mineralogy and isotopic composition also fit Mars, placing it among the small, rare class of Martian meteorites, rocks blasted off Mars by large impacts that later fell to Earth. In the mid-1990s, ALH 84001 became world famous when a research team reported several intriguing features. Tiny carbonate globules with distinctive zoning. Microscopic structures that some interpreted as resembling fossil bacteria. Magnetite grains and certain chemical patterns they argued were hard to explain without biological activity. The team suggested that ALH 84001 might contain evidence of ancient Martian microlife. The claim was cautious but electrifying. It forced scientists to sharpen their tools for distinguishing abiotic, non-biological, from biotic, biological, signatures. Over the following years, many of the features could be reproduced by non-biological processes. The original life interpretation remained controversial and is not considered proven. Yet, even without a confirmed biosignature, ALH 84001 had a profound impact. It showed that rocks from other planets can naturally travel between worlds, carrying detailed chemical and textural information. It pushed forward techniques for analyzing microscale features and isotopic ratios in planetary materials. It demonstrated how carefully the scientific community treats any claim of extraterrestrial life, demanding multiple, independent lines of evidence. ALH 84001 is now seen as a training case, a demanding test of our ability to separate geology from biology, a skill that will be vital when we analyze samples from Mars, icy moons, or other small bodies in the future. Closing thought for this segment. Together, Allende, Murchison, Canyon Diablo, and ALH 84001 show how small, dark stones can transform big ideas. Allende fixed the age of the solar system and revealed the earliest solid grains. Murchison proved that complex organics form in space and can be delivered to planets. Canyon Diablo linked meteorites to impact craters, changing how we see planetary surfaces. ALH84001 brought the search for life on Mars down to a fragment you could hold in your hand. Every meteorite is a message, but some speak louder than others. Each one we study refines the story of where we came from and what might be possible elsewhere. When we talk about the origin of life, it is tempting to picture everything happening on Earth: warm ponds, lightning storms, deep-sea vents. But part of that story begins far from here, in tiny worlds that never became planets. Meteorites, especially the dark, fragile class called carbonaceous chondrites, are physical proof that rich organic chemistry was already underway in space long before the first cell appeared on our planet. These meteorites are, quite literally, rocks that contain carbon-based molecules. When scientists crush and carefully extract material from carbonaceous chondrites in ultra-clean laboratories, they find a zoo of organic compounds. There are amino acid-alike molecules, including many varieties that are rare in biology or appear as mixtures of left-handed and right-hand forms rather than the single-handedness life prefers. There are aromatic hydrocarbons, with ring-like structures similar to those in many organic solvents and pigments, and aliphatic chains that resemble the long carbon backbones in oils and waxes. Nitrogen-bearing organics are present too, linking these meteorites to the kind of chemistry that can eventually give rise to nucleobases and other biologically relevant molecules. It is crucial to be clear, these molecules are not life. They do not show metabolism, replication, or evolution. But they are many of the same kinds of building blocks that life assembles into proteins, cell membranes, and more complex structures. Finding them locked inside stones that predate Earth's oldest fossils tells us that the raw ingredients for biology are not unique to our planet. They emerge naturally when you mix rock, ice, radiation, and time. How do such molecules form in the first place? The story begins before there were meteorites at all, when the solar system was still a cold disk of gas and dust around a young Sunday. In that disk, tiny mineral grains acquired thin mantles of frozen water, carbon monoxide, carbon dioxide, methane, ammonia, and other simple molecules. These ice-coated grains drifted through regions bathed in ultraviolet light from the young sun and energized by cosmic rays from the galaxy. Every photon or charged particle carried enough energy to break some chemical bonds and allow atoms to recombine in new ways. Over thousands and millions of years, those surface reactions stitched simple molecules together into more complex organics, first small chains, then larger, tar-like macromolecular material. Later, as dust clumped into larger bodies, kilometer-sized asteroids and their precursors, the chemistry changed again. Inside some of these objects, radioactive elements and the heat of formation warmed the interior just enough to melt ice into liquid water for a time. That water percolated through pores and fractures, reacting with minerals and existing organics. In this mild, low-temperature water rock laboratory, some molecules were altered, others were created anew, and the overall organic inventory grew more complex. When the internal heat source faded and the water froze or escaped, the chemistry slowed and finally stopped. What remained was a solid record, a rock whose minerals, isotopes, and organic content preserve a snapshot of conditions inside a small body more than 4 billion years ago. Meteorites are pieces of those ancient laboratories that have been broken off, sent wandering, and eventually delivered to Earth. Once they land, and once we recover them before terrestrial weather and biology erase the signal, they let us rewind that chemical history in extraordinary detail. We can measure the exact mix of amino acid-like compounds, compare their handedness, identify nitrogen and sulfur functional groups, and look for relationships between mineral alteration and organic complexity. In effect, each meteorite is a sealed archive of experiments that nature ran in countless icy rocks long before our planet stabilized. The connection to early Earth comes through impacts. In the first few 100 million years of solar system history, Earth did not evolve in isolation. It was bombarded by debris left over from planet formation, asteroids, comets, and smaller fragments whose orbits were disturbed by the growing planets. Among these were many carbonaceous bodies loaded with water and organics. When they struck Earth, some fraction of their volatile content was destroyed by the enormous heat of impact, but not all of it. Smaller impactors, shallow entry angles, fragmentation high in the atmosphere, and subsequent gentle deposition into oceans or sediments would all have allowed part of that organic cargo to survive. Over tens of millions of years, this steady rain of material could have delivered substantial amounts of carbon-bearing molecules to Earth's surface. At the same time, the planet was running its own chemistry, volcanic gases reacting in the atmosphere, minerals interacting with water along mid-ocean ridges and in hydrothermal systems, lightning and UV light driving reactions in shallow pools. The most realistic picture is not a single source of life's ingredients, but a web of contributors. Internal geochemistry provided some components. Meteorites and small asteroids delivered others, especially complex organics pre-assembled in space. Comets may have added still more volatiles and exotic molecules. Meteorites are our strongest evidence that this external contribution was chemically rich. They show, in hard numbers and lab spectra, that complex organics were already present in the building blocks of the planets. They demonstrate that amino acid, like molecules and other prebiotic compounds, can emerge in environments very different from Earth's surface, inside small, dark, water-altered rocks, far from any oceans or atmosphere. That realization changes the emotional meaning of holding a meteorite in your hand. You are not just touching an ancient stone, you are touching matter that took part in chemical stories older than life, stories that may have supplied some of the first words in the language biology eventually learned to speak. In that sense, meteorites narrow the gap between out there and in here. They remind us that Earth's early chemistry did not start from scratch with pure, simple molecules. It began on a planet already dusted with complex organics forged in deep space and processed inside forgotten worlds. When we grind, analyze, and catalog these fallen stones, we are, in a very literal way, reading the first drafts of life's recipe, written in ice and dust, long before any living thing could read it. In the end, it always comes back to a single stone in a human hand. We return to the quiet desert, or to the blue-white light of Antarctica. The wind has dropped. Daylight is flat and bright, and in the palm of a gloved hand lies a small, dark rock with a thin, melted rind. Nothing about the landscape explains why it is here. It is heavier than it looks. Its surface is pitted where droplets of molten material once streamed away in the air. It is, in every sense, out of place. That out-of-place feeling is the point. This stone did not weather on this desert floor, or freeze in this Antarctic ice. It cooled in the dark of space, orbiting the sun long before there were continents, oceans, or trees on Earth. Before our planet finished assembling, the atoms inside this meteorite were already beginning their unquiet story. Some meteorites are fragments of shattered protoplanets, cores, mantles, and crusts broken apart by ancient collisions. Iron meteorites carry the textures of slowly cooled metal from deep inside differentiated worlds. Pallasites preserve a boundary layer of green olivine crystals suspended in nickel or iron, like a cross-section through the interface between rock and core. Achondrites are igneous, pieces of crust and mantle that once flowed as lava on small bodies whose surfaces have long since been destroyed. Others are far more primitive. Carbonaceous chondrites look like soot-black concrete under the microscope, bright chondrules set in fine, dark matrix, studded with tiny refractory inclusions. They are as close as we can get to raw material from the solar nebula, dust and ice only gently processed by heat and water inside small parent bodies. In these rocks we find water-bearing minerals, complex organic molecules, and tiny time capsules like CAIs that fix the age of our planetary system at about 4.5 billion years. A few meteorites carry more specific return addresses. Lunar meteorites match the chemistry and mineralogy of Apollo samples so closely that we can be confident they were blasted off the moon by impacts and later fell onto Earth's surface. Martian meteorites lock away bubbles of gas whose composition matches the thin atmosphere measured by landers on Mars. In your hand, such a stone is not just from space. It is a loose fragment of another world we have only begun to explore. Threaded through many of these samples is carbon chemistry of surprising richness. Within some dark, fragile meteorites, laboratory work reveals amino acid, like molecules, aromatic rings, nitrogen-bearing organics, and long, complex carbon networks. These are not fossils of life, and they are not evidence that biology began somewhere else and arrived fully formed. They are, instead, proof that the building blocks of biochemistry can arise naturally on dust grains and within small bodies wherever there is ice, radiation, and time. Meteorites show that long before Earth had stable oceans or continents, space was already busy writing its first chemical sentences. For early Earth, these falling stones were not rare curiosities. During the heavy bombardment and its long decline, countless carbonaceous asteroids and smaller bodies struck our planet. Many of their organics and volatiles were destroyed in fireballs, but not all. Some fractions survived in cooled fragments that landed in water, soil, or hydrothermal systems. Alongside internal processes, volcanic gases, deep-sea vents, lightning in a young atmosphere. Meteorites helped stock the planet with an initial inventory of water and carbon chemistry. They were couriers, not authors, of life's story. But without couriers, the story might have read very differently. So when we classify a meteorite and give it a catalog number, we are doing more than filing another specimen into a museum drawer. Each sample adds lines to a growing chronicle. How the first solids condensed in the disk around a young sun. How small bodies melted, differentiated, and were shattered. How water and carbon compounds were stored, processed, and delivered. How similar processes might play out around other stars, in other planetary systems. In a display case or on a lab bench, a meteorite can look unremarkable, a dark lump with a tag. But its metal crystals grew as it cooled over millions of years in the deep interior of a lost world. Its minerals trapped water and heat in small, transient oceans within an asteroid. Its organics formed in ice mantles long before any cell divided on any planet. When you hold such a stone, you are touching a fragment of a broken world and, at the same time, a physical page torn from the first chapter of our own. These are the messages that fell from the sky. We are still learning how to read them.